Hello everyone, this is Abdurrahman Usama. Today we will have our fourth tutorial. We will discuss RSA encryption and decryption. Let's start with our first question. The question says, perform encryption using RSA algorithm for the following. So, as you can see here, we have some givens. Let's discuss each one of these variables and understand what it is. So, the first two values, P and Q, are two randomly chosen prime numbers. Okay, the third one here, the E, is our public key, and the last one here, M, is our message, the message that we need to encrypt in this case here. So, how do we encrypt using RSA? So, the first step we need to do is to get a variable n. N equals to P multiplied by Q. So in our case here, it's 3 multiplied by 11, which is 33. The next step is to do the actual encryption. So the RSA encryption is done as follows. To get the C, which is our ciphertext, we do M power E modulus N. So in our case here, C is equal to 5 power 7. 5 is our message and 7 is our E, M power E, modulus N, which is 33. Okay, so here C is equal to 14. If you don't remember how we do the modulus, if you want to do it using the calculator, what you do is you get the first value here divided by the second value here, then you get the like I will give you an example on this one. So it's 5 power 7 divided 33. This is equal to 367.424242. So what I will do now is that I will take the decimal part, which is 0.424242, and I will multiply it by 33. So it will be 0.424242 multiplied by 33, which is the second value here, the one after the modulus. This will be equal to 14, which is our value here. This is a quick reminder on how to calculate the modulus. Let's go to the second question. Here we want to do an RSA encryption also, using the values P equal 5, Q equal 17, E equal 3, and message equal 9. The first step that we will need to do is to get the N. So N equals to P multiplied by Q, which is equal to 5 multiplied by 17, which is equal to 85. So now we get our ciphertext. So C is equal to the message power the public key modulus the N. And this is equal to, our message here is equal to 9. So 9 power 3. Note here, this is not a D, this is a E. A D here means it's a private key. It works just the same like E. So here we have the public key to encrypt to use in encryption. So it's M power E modulus N. So it's 9 power 3 modulus N, which is equal to 85. Pardon me. what we are doing now, it's n power 3 modulus n, which is equal to our message here, which is 9 modulus 3, 9 power 3 modulus n, which is equal to 85. This one here was equal to 85. So this is equal to 8. Sorry, this is equal to 49. Now with the third question here. So here we have P equals 7, Q equals 5, and D equals 17. We don't have an E here, we have a D, which is a private key, and we have our message equal to 8. So we start by getting our N equals to P times Q, which is equal to 7 multiplied by 5, which is 35. Now we get our ciphertext, which is equal to the message power D now here, modulus N equal to, so our message here is 8, and our private key here is equal to 17 modulus 35. This is equal to 8. And this is it. Now with the second question, here comes the hard part. Now we want to decrypt RSA. So let's start by reading the question. The question says, perform decryption using RSA algorithm for the following. So what are the givens here? We have our P and Q, which are the two prime numbers. We have E as the public key, and we have the ciphertext instead of the message. So this is the ciphertext that we want to decrypt in this case. So you have to follow me carefully during this answer, as the question might be a little bit tricky, but in fact systematic. So the first step that I will do here, I will get my N. So let's start by just showing you what I want to do at the end. So I want to get the message M. M here is equal to C power D modulus N. This is how I get my message here. So what do I have here in order to do this? I have C, the ciphertext. N, N is easy. So how do we get N? We do N equal to P multiplied by Q, which is in this case here is 11 multiplied by 13, which is equal to 143. So now I have C and N. What I don't have here is D. So this is the problem here. It's that I don't have D. So how do we get D here? We will use something called the Euclidean algorithm. Let's start by showing you an equation that we will need to use in order to get our values here. So the equation is as follows. It's E multiplied by D, which is the public key multiplied by the private key, equals to 1 plus K, which is just a variable within the equation, multiplied by something called the Euler quotient. So how do we get this Euler quotient? It's very, very easy. So Euler quotient is equal to P minus 1 multiplied by Q minus 1. So in our case here, it's 10 multiplied by 12, which is equal to 120. So let's try to fill in this equation here. We have our E, so we can substitute here. So it's E multiplied by D, we don't have D here, so it will stay the same. This is equal to 1 plus K, we don't have K, so it stays as it is, multiplied by Euler's quotient, and we have it now, so here it's 120. Now, as you can see, we have a problem. We have one equation with two unknowns. So in order to solve this problem or this equation, we need to use an algorithm that is called the Euclidean algorithm. So bear with me because this might be a little bit weird, but it's so systematic, so it should be easy at the end. So let's start here by writing our equation, the one we just wrote here before. It's 11 multiplied by D equal to 1 plus K multiplied by 120. So the first thing we need to do in order to start solving our Euclidean equation is that we change the form, or we substitute with the variables in here, the one next to the D and the one next to the K, in a new equation. So how do we do this? We do the following. 1 equal 120x plus 11y. And we can change here, it can be 11x plus 120y, doesn't matter. It's just for a representation. So we start the equation by doing the following. It's a little bit weird, so bear with me. So the first thing, let's just give you an overview about how this equation works, or what is this equation technically. So this kind of equation is called a Diophantine equation. Okay, a Diophantine equation is an equation with two or more unknowns. In our case, it will always be two unknowns, and this equation may have more than one solution. It has several solutions. Some are real and some are not real solutions. So there might be some complex solutions that we don't care about, and there are some integer solutions that we care about. So when we use the Euclidean algorithm, we only get one solution, and we only care in our case here for only one solution. So the strategy that we use in the Euclidean algorithm is basically dividing the value here by the one here. We divide a by b, and we get the quotient and the remainder. Okay, and we keep doing this till the remainder is equal to 1. So let me show you how we do this. Let's start with the two values here, 120 and 11. We get the 120 here, and we put equal 11, and we open an empty bracket now here, and we do a plus sign, and we leave the right side here empty. So what we do here, we will do 120 divided by 11. So this is equal to 10. This is an integer division. And now we do 120 modulus 11 to get the remainder. And here the remainder will also be equal to 10. Okay? So we keep doing this. We keep doing the thing I just did here till we reach a remainder here that is equal to 1. So what do we do in the next step? We don't care about the value inside the bracket. We don't change anything inside the bracket. We care about the value here. So here, this one, we assume that it has a bracket which is equal to 1. To understand the concept, we don't multiply the bracket with the value outside, because the bracket will relate to the final answer. So we take the 10 and the 11. So 11 equal to 10, an empty bracket here, plus an empty side here. So 11 divided by 10 is equal to 1, a modulus division also. And 11, an integer division, sorry. So 11 modulus 10 is equal to 1. As you can see, we've reached a remainder of 1 here. So the next step that we do, now as you can see, we have two equations. This is equation 1 and this is equation 2. The next step that we do here is that we rewrite the two equations in the form that the remainder is on the left side. Just like this. Let's start with the first equation. It's 10 equal to 120 minus 11 multiplied by 10. And the second one will be 1 equal 11 minus 10 multiplied by 1. So we just we just rewrote these two equations. These are exactly the same as these ones. So the next step here is that we keep substituting the equations from up till the from the very last one till the first one. So since we have two equations only here, we substitute this one into this one. How do we do this? We substitute the value 10 here into this value 10 here, meaning that the second equation will be rewritten as follows. It will be 1 equal 11 minus, I will open a bracket here, and I will substitute this 10 with this equation here, which is 120 minus 11 multiplied by 1, and all this will also be multiplied by the one here that was next to the 10. So let's push in the negative sign here. So it will be 1 equal 11 minus 120 minus 11, 1. Okay, so now we want to combine the like or similar values. Now, as we said, we do not multiply anything into the brackets. And here we check when we say we want to find similar values, we check the values outside the brackets. So here we can assume that this 11 is 11 multiplied by a bracket including 1. So we can merge this 11 with this 11 here. So basically, okay, pardon me, I may have done something wrong. This here was 11 multiplied by 10, not 1. So it's here 11, 10, and here 11, 10. So basically, when I combine these two 11s, here, this and this, I will just do 11. I will assume that I have 11 and 1 and 11 and 10. So basically, it will be 1 equals 11 and 11. I will just add the values here together. Then I will do just minus 120. Okay, so far so good, I hope. So now we have substituted all the equations together since we only have two here. Let's try to rewrite this equation just to make it close to this one or this one. It is already close to this one. So I will make it close to this one. It will be 11 multiplied by something, which is here 11, 11. And what I will do next here, I will push the other things to the other side. So it will be equal to, I will push the 120 to the other side. It will be 1 plus 120. So this word was 11 multiplied by d equal to 1 plus k times 120. What do you think would be here the d, and what would be the k in this equation? As you can see, it's almost, it's similar or it's exact to this one. So here, this bracket should contain the d. So d will be equal to 11. And here, since 120 does not have anything next to it, so it means that k is equal to 1. And that's it. We have solved the Euclidean equation or the Euclidean algorithm. Now with the last step, which is the thing that we actually need for the question, we need to decrypt. So now we have our D, which is equal to 11, and from the first slide back here, we had our N, which is 143. So N is equal to 143, and we have the rest of our variables here. Let's rewrite the equation to get the message. So M is equal to C power D modulus N. In our case here, it is 106 power D, and D here is 11 modulus N, which is 143. So there is a small trick here. So basically, if you try to write this on your calculator, you will not be able to solve it, as the values are huge. 106 per 11 is huge. So what we can do here is we can split the modulus. How do we do this? We split this part. So it's 106 power 11. We can split it into 3, for example. It can be split into other forms. So what I can do here, I can do 106 power 4 modulus 143, and I will multiply this with 106 power 4 modulus 143. Now I've done 8 out of 11, so what I have left is 3. So I will multiply again with 106 power 3 modulus 143, and after I do all this, I do again a last mod here, 143. As you can see here, the summation of these 3 powers here is equal to 11 here. So this modulus, if I try to solve it, this part will get me 3 multiplied by this part here, which will get me also 3 multiplied by the last part here, which will get me 112. So when I get all these 3 and multiply them together, I do modulus 143, one outside here, and this will get me 7. So the message here is 7. And that's it for the first question. So let's start with the second question here. So now we have P equal 17, Q equal 31. We have the public key equal to 7 and the ciphertext equal to 128. And we want to do the same, just like the first question. We want to decrypt using RSA algorithm. So the first thing that we need to get is the N. We get our N, which is P multiplied by Q. So it's 17 multiplied by 31, which is equal to 527. And we get our Euler totient, which is Euler totient of N, which is P minus 1 multiplied by Q minus 1, which is 16 multiplied by 30, which is equal to 480. Now we write our equation, which is E multiplied by D equal to 1 plus K multiplied by Euler's totient of N. So we try to substitute here. We have the E equal to 7, so it's 7 multiplied by D equal to 1 plus K. We don't have K, so it's K multiplied by Euler's totient of N, which is 480. So just like the first one, we have an equation containing two unknowns and we need to solve it. So we go to the Euclidean algorithm. So I will just rewrite the equation here. It's 7 multiplied by d equal to 1 plus k multiplied by 480. So let's rewrite it just like the last one. So it is 1 equal 480x plus 7y. Okay, so we start by doing the same. We get the bigger value, or this value here, it's 480, equal 7, the smaller value, which is the one here, and we open a bracket here and leave this plus empty. So 480 divided 7 is equal to 68. 480 modulus 7 is equal to 4. And we do it again using the numbers here outside the bracket, not the 68, it's the 7 and the 4. So it is 7 equal to 4. We open a bracket here, we add the plus sign. So 7 divided by 4, an integer division, remember, so it's 1. 7 modulus 4 is equal to 3. And here we did not reach a remainder of 1 yet, so we do it again. 4 equal to 3, open a bracket, plus. So 4 divided by 3 is equal to 1, and 4 modulus 3 is equal to 1. So as you can see here, we've reached 1 here on this side as a remainder. So what we do next here, we rewrite our three equations here. We have equation 1, equation 2, and equation 3. We rewrite them such that the remainder is on the left side. So it is 4 equal to 480 minus 7 multiplied by 68, and 3 equals to 7 minus 4 multiplied by 1, and the last one is 1 equals to 4 minus 3 multiplied by 1. So the next thing is we keep substituting the equations into each other. So basically we substitute this one into this one, the second one into the third one. So what we can substitute is the remainder here into this 3. So it will be equal to 1 equal to 4 minus, we substitute the whole equation here in the 3. So it's 7 minus 4 multiplied by 1, all multiplied by 1. So this equation here, after we expand here the sign, so it will be 4 minus 7 plus 4 multiplied by 1, correct? So here it will be 1 equal 4 minus 7 plus 4, 1. So let's try to combine the similar values. So we only have here 4 and 4, 4 multiplied by 1 and 4 multiplied by 1. So it will be 4 multiplied by 2. We add the brackets and we assume here we have a bracket with 1. So basically it will be 1 equal to 4 multiplied by 2 minus 7. So far so good. So now we try to substitute with the last equation, which is equation 1 here. So we substitute the 4 here with this 4. So basically it will be 1 equal to 480. We open a bracket, 480 minus 7 multiplied by 68, all multiplied by 2. And this is minus negative, this is minus 7. as it is. So what we do here, we want to multiply this two value here into these two values. And remember, we never change the values outside the brackets. So what we do here is as follows. It will be 1 equal 480 multiplied by 2. We cannot change the 480 here, so it will be 480 multiplied by 2, just like that, a bracket next to it, minus 7 multiplied by 68. We can multiply with the 68, no, not the 7, so it will be minus 68 multiplied by 2 is 136, so it will be 136 and minus 7. So we combine like terms, so we have 7 and 7 multiplied by 136 and 7 multiplied by 1, so it will be 1 equal 480 multiplied by 2 minus 7 multiplied by 137. Okay, so far so good. We are done with substituting equations into each other. So now we have this equation here. We want to make it as similar as possible to the one up here. So let's start by doing this. So we have the 7. The 7 should be alone on its side. So it can be as follows: 1 minus 480 multiplied by 2 equals to negative 7137. So now we have a small problem, which is the negative here and the negative here. As you can see, there is no negative here outside and no negative here. So obviously these signs relate to the output that was the D and the K. So in order to rewrite it the right way, we do the following. It will be 1 plus, instead of having minus here, 480, it will be plus 480. And we will add the sign inside the bracket, like this. Equal to 7. And we will also add the sign inside the bracket, so it will be 137, just like this. So if we want to compare the values here with the values next to the 480, next to the K and the D. So 480 has the K next to it, which is the negative 2. So K is equal to negative 2. And we have the 7 next to it, the D. So the 7 has next to it the D, which is negative 137. So D is equal to negative 137. Now we have a small problem. It's that we can't have D as the negative number. Okay. Wait a second. Not this again. Oh God. Okay, we can't have the D as a negative number. So basically what we do here is a very small trick. Whenever we have the D as a negative number, we get D as follows. D will be equal to the value here, the negative value, which is 137, plus Euler's totient, which was P minus 1 times Q minus 1. In our case here, Euler's totient was 480. So the D here will be negative 137 plus 480, which is 343. This will be our D, which is our private key. So let's start with the decryption process itself. So M, which is the message that we want to get, is equal to C power D modulus N. So this will be equal to C is our ciphertext, which is 128 power D, which is 343, and this is modulus n, and n here was equal to 527. So what do you think we do here? Obviously it's extremely hard to solve such huge equation. So we do just as we did in the last one. We split this into smaller modulus equations. So we can just split this into different 128 power 64 modulus 527, or 128 power 32 modulus 527, and we multiply them all together, and the final value is also done. We do the final multiplication value modulus 527, and we get our final result for the message M. In this case here, this will be equal to 2. Okay, so just follow the exact same steps as we did in the previous one. If you are not able to get the correct result, you can just ask me in the interactive session to do it with you. Okay, now with the third question. So here it says, in a public key system using RSA, you intercept the ciphertext C equal 10 sent to a user whose public key is E equal 5 and N equal 35. What is the plain text M? So here we have as given the ciphertext, which is 10, and we have the value of E, and we have N. Remember, N was equal to P multiplied by Q. Okay, so what we don't have is Euler's quotient of N, which is P minus 1 multiplied by Q minus 1. So now we have a problem. It's that here we have the value of N, which is 35, but we don't have the value, we don't have the value of the P and the Q. So here, remember that P and Q are two prime numbers. So there is only one solution for this problem. We get the values of P and Q by trial and error. We find two prime numbers whose multiplication is equal to 35. So in this case here, I found P equal to 7 and Q equal to 5. So in order to get Euler's quotient, we do 6 multiplied by 4. So Euler's quotient will be equal to 6 multiplied by 4, which is equal to 24. So now we have our E, we have our Euler's quotient, so we can start formulating our equation. So the equation here is E multiplied by D equal to 1 plus K multiplied by Euler's quotient of N. So here A is equal to 5, so 5 multiplied by D equal to 1 plus K, we don't have K of course, multiplied by 24. Okay, so we rewrite this into our Euclidean algorithm equation. We will use the Euclidean algorithm since we have two unknowns in one equation. So it will be 1 equal to 24x plus 5y. So let's start solving our equation. I will just rewrite it here. It's 5 multiplied by D equal to 1 plus k multiplied by 24, and this was 1 equal 24x plus 5y. So let's start doing our Euclidean algorithm. So we start by getting the larger value here. It's 24 equal to 5, open brackets and the plus sign here. So 24 divided by 5 is equal to 4. 24 modulus 5 is equal to 4. We do the same with the 5 here and the 4 here. So it's 5 equal to 4. We open the brackets. 5 divided by 4 is equal to 1. 5 modulus 4. The remainder here is 1. So since we have reached the remainder 1, we stop and we start by rewriting the two equations so that the remainder is on the left side. So 4 equal to 24 minus 5 multiplied by 4. We have 5, sorry, it's not 5, so we have 1 equal to 5 minus 4 multiplied by 1. So these are our two equations. We start by substituting the first one into the second one. So we substitute this equation here with this 4 here, since this is equal to 4. So it's 1 equal 5 minus 24 minus 5 multiplied by 4, all multiplied by 1, which was this one here. So we open up the bracket, we multiply by the we multiply by the sign. So 1 equal 5 minus 24 plus 5 multiplied by 4. We combine the like terms, so it will be equal to 1 equal, remember 5 here, we assume that it's 5 multiplied by bracket with 1, and this is 4, so it will be 5 and 5, just like that, minus 24, and we're done with substituting the equations into each other. We now rewrite the equation so that it's similar to this one. So in our case here, it will be 5 equal to 1 plus 24, and now this is similar to this one. So we can easily get the d, which is the one next to the 5 here, and the k, which is the one next to the 24 here. So we have our d as 5 and our k as 1. This is it. So we have d equal 5, k equal 1, and we have our n here, so we can easily get the message. So basically, message is equal to c power d modulus n, which is equal to our ciphertext is 10, so it's 10 power 5 modulus n, and n is 35, and this is equal to 5. So our message here is equal to 5, and that's it. Hope it's easy. Now with our fourth question. So here we also want to perform a decryption using RSA algorithm. We have our values P and Q. We have E equal 7, and we have C, which is the ciphertext, equal to 59. So let's start by getting n. N is equal to P multiplied by Q, which is equal to 7 multiplied by 11, which is equal to 77. Okay, and we get our Euler's quotient, which is equal to P minus 1 multiplied by Q minus 1, so it's 6 multiplied by 10, which is 60. And we know that the equation is E multiplied by D, which is equal to 1 plus K multiplied by Euler's quotient of n, which in our case here is equal to E. We have E as 7, so 7 multiplied by D, which is the private key, equals to 1 plus K multiplied by Euler's quotient, which is 60. So we have one equation and two unknowns, so we need to do our Euclidean algorithm. Let's rewrite this here. So it's 7 multiplied by D, which is equal to 1 plus K multiplied by 60. We rewrite this as 1 equals 60x plus 7y. We start our Euclidean algorithm, which is 60 equals to 7 multiplied by something plus something. So 60 divided by 7 is equal to 8, and 60 modulus 7 is equal to 4. Then we do the same with 7 and 4, since we did not reach a remainder of 1. So 7 equal 4, open a bracket here, plus empty side here. So 7 divided by 4 is equal to 1. 7 modulus 4 is equal to 3. We do the same again. So we have 4 equal to 3 brackets plus 4 divided by 3 is equal to 1. And 4 modulus 3 is equal to 1. So we are done. We have the three equations. This is the first one, the second one, and the third one. So what we do next, we start by rewriting our equations with the remainder on the left side. So they will be as follows: 4 equal to 60 minus 7 multiplied by 8. Then we have 3 equals to 7 minus 4 multiplied by 1. And we have 1 equal to 4 minus, we have 1 equal 4 minus 3 multiplied by 1. So we have reordered the equations. We start by substituting the second one into the third one, then the first one into the combination of the second and the third one. So we substitute here this equation, which is equal to 3, into this one here. So it will be 1 equal to 4 minus, we open a bracket, it will be 7 minus 4 multiplied by 1, and all multiplied by 1 outside here. So we open up the brackets here by multiplying the negative sign. So it will be 1 equal 4 minus 7 plus 4 multiplied by 1. So we combine the 4 here and the 4 here. So it will be 1 equal 4 multiplied by 2 minus 7. So the next step, we use the first equation here and combine it with the combination here. So 4 here can be combined with, or you can substitute this 4. So basically, let's write it down here. It will be 1 here, the 1 here, equal to, we substitute the equation instead of the 4. So it's, let's open a bracket, it's 60 minus 7 multiplied by 8, all multiplied by 2 here minus 7. We multiply here this 2 inside. So basically, what do you think we will do? So what we do here, it will be 1 equals 60 multiplied by 2, and then we have here the 7, we'll say as it is, so it's minus 7, and we multiply the 2 by the 8 inside the brackets, so it's 16, and we have the minus 7 here. So we combine like terms, so it's equal. So we combine the 7 here and the 7 here, so it's 60 multiplied by 2 minus 7 multiplied by 17. So now we are done with combining the 3 equations. Now we try to make this one similar to the equation up here. So basically we do the following. It will be 1 plus 60, and since I will get this one into the other side, it will be negative. It should be negative 60, but I will just since we don't have a negative sign here, so I will add the negative inside the bracket, so it will be negative 2 here, and this will be equal to, it should be negative 7 multiplied by 17, so I will push the negative sign inside the bracket, so it's 7 multiplied by negative 17. Now this is similar to this one. So we have next to the 7 the d, which is negative 17, and we have next to the 60 the k, which is negative 2. So we have k as negative 2, d as negative 17, and remember we can't have d as a negative value, so to get the d we do negative 17 plus the Euler's quotient, and the Euler's quotient here was equal to 60. So negative 17 plus 60 is equal to 43. So our d here is 43. So to get our m, we do m equal c power d modulus n, which is equal to 59 power 43 modulus n here was equal to 77. So this gets us an m of 31. That's it. And just as we said before, 59 power 43 modulus 77 may be a bit big, so we can just split it into smaller modulus equations and combine them at the end. Now with the 5th and the last question for this tutorial. So we want to perform decryption using RSA algorithm. So the question says, in an RSA system, Alice's public key E is equal to 5 and N is equal to 851, and discover their corresponding private key. So remember here, just as the one of the previous questions, we have here E equal to 5 and N equal to 851. The problem here is we only have N as a given, we don't have P and Q, so we are not able to get our Euler's quotient. So what we do here, we get P and Q by trial and error. We try to find two prime numbers whose multiplication is equal to 851. So I will just give you the values here. So P is equal to 23, Q is equal to 37. So you can Google it, guys, but there is really no systematic way in order to find P and Q for a value N. But remember, the thing that makes it easier here is that you know that P and Q both are prime numbers. So you only search through prime numbers. So now that we have our P and Q, we can get our Euler's quotient of N, which is equal to P minus 1 multiplied by Q minus 1. So it's 22 multiplied by 36, which is equal to 792. So now we have our E, N, and Euler's quotient. Now we use the Euler's quotient and E to formulate our equation. So it's E multiplied by D, which is equal to 1 plus K multiplied by Euler's quotient of N. So we substitute with the Euler's quotient and the E. So we have 5 multiplied by D, which is equal to 1 plus K multiplied by Euler's quotient, which is 792. So let's rewrite this here. 5 multiplied by D, which is equal to 1 plus K multiplied by 792. Pardon me. Okay, so let's rewrite the equation just as we always do. It will be 1 equal to 792x plus 5y, and we start solving the equation. Note that you do not need to do this step here. It just makes it easier to read when doing the Euclidean algorithm. You can just skip this step if you want. So it's 792 equals to 5 open brackets plus, so 792 divided by 5 is equal to 158. This is 8 here. And 792 modulus 5 is equal to 2. Now we take 5 and 2, so 5 equals to 2 brackets, and then this. So 5 divided by 2 is equal to 2, and 5 modulus 2 is equal to 1. So we've reached the remainder of 1, so we can stop. Now we have our equations 1 and 2. So let's start by rewriting the equations to have the remainder on the left side. So it's the first one will be equal to 2 equals to 792 minus 5 multiplied by 158. And the second one will be equal to 1 equals to 5 minus 2 multiplied by 2. Now we substitute the first equation into the second equation. So it will be 1 equals to 5 minus, I'll substitute in the 2 since the remainder here is 2. So the 2 outside the brackets, remember this. So it's 792 minus 5158 all multiplied by 2. So let's do the multiplication here. So let's solve this bracket. So it will be 1 equal 5 minus 792 multiplied by 2. Remember, we don't change the value outside, so it's 792. We don't change the value outside the bracket, so it's 792 multiplied by 2, just like this. Minus, we don't change the 5 since it's the outside the bracket, so we do the multiplication inside the bracket. So it's 158 multiplied by 2, so it's 316. And that's it. We have solved the equation together. We've substituted the equations into each other. So now we combine like terms. So we have 5 and 5. So it's 1 equal 5 remember, we forgot to do something. We have to multiply the value here, the sign here, into the brackets. So it's 1 minus 792 multiplied by 2 plus 316. So when we combine these, we have 5 multiplied by 317 minus 792 multiplied by 2. So now that we are done with combining like terms, we try to rewrite this equation to make it similar to this one. So basically it will be 5 multiplied by 317 equal to 1 plus 792 multiplied by 2. So now we know that our private key, which is D, is equal to 317, which is the one next to 5 here, and we know that our E is equal to 2, which is the one next to the 792 here. Sorry, this is the K next to the 792 here. And that's it. We are done with our tutorial. See you next tutorial. Thank you.